it would be nice to improve the audio of the video, but there's no way to improve audio, to be honest. Okay. I think audio quality is not good, but I think yeah, there's no way to improve the audio. Yeah. So 我现在学习中文。现在那个人工智能的发展很大很快，所以如果我一直靠那个人工智能那个翻译成中文，那个翻译成英语的时候，我的中文水平我的水平有提高。所以如果你一直靠人工智能的话，我的中文一样不能进步，所以我真的没有没有语言能力，所以现在我每天花30分钟学习中文，但是真的很难。那个我的感觉是真的那个学入你学心就不进则对。So 一样的学习理论物理是一样的，一样的。So 慢慢的学习。So 现在140个学生们选择我的课，但是期末我不知道几个学生。Anyway, so let's do it step by step, and then let's do it slowly, and then let's see, let's keep it up like till the end of the semester, slowly. Otherwise, okay, I'm sorry, you don't understand the Chinese. Anyway, my Chinese native Chinese do not understand my Chinese, so don't worry. And let's do step by step, and then stick till the end of the semester how much we can learn. Okay. So last time, canonical ensemble, microcanonical ensemble and canonical ensemble. Let's do a little bit review canonical ensemble. Okay, so canonical ensemble to get the probability we might. So we look at the try to maximize the probability by equality. This is Lagrange multiplier. U is the state, W is the probability, and then F is the free energy. And we try to maximize free energy to get the probability. And then and of course, this one is equal to sum of W. Okay. So, and then if you maximize it in terms of the probability, and then you get the difference. It's used like ADT. Okay, so that's what we get. And then from here, one can obtain that the W nu is the E3 minus epsilon plus minus lambda ABT, and then plus minus 1. And then to satisfy B to minus epsilon nu, ABT over Z. Okay. And then Z is equal to G is partition, the sum of the partition. This is equal to E to minus lambda Okay, so that's what you get. Okay, so then okay, so then plug this one back into there. What you get is F is equal to minus later, what was KBT? Oh, sorry, KBT. And you free energy, you get the free energy. Okay. So that's what you get from the analysis. Yeah, plug. So the last time we plug this one into here, and then we see that the this is exactly equal to the partition function like this. That's so if you start with the following notation, so we sum over nu log sorry w nu log w nu. Okay. So we mentioned that the entropy, statistical mechanical entropy, in the one student question that to derive this one we have assumption to derive this one we have assumption S E T T sum of the and w nu. So we assume, and why we assume like this? So that there's a question. So I have a bit better understanding of. So the entropy is really, I mean, intrinsically statistical mechanical quantity. It's not like a dynamical quantity like energy and so on. So it's really entropy is statistical mechanical quantity. So therefore, it should be written in terms of probability. So that's one way to. A little bit better answer than I don't know the answer mentioned answer. So it's really entropy that's really intrinsic purely statistical interpretation. That's one way to answer the question. Yes. And if first of all, if you plug on this one into here, what's going to happen? We can take a look. So if you take into heavy sum over nu, and plug that one into here. Okay. And then sorry, am I doing correct thing? And then plus. Okay, so this is what you get from this. So here, and then if you do that, so this is so if you so here this is just the average of energy. So you get the average of energy. So from here, what you get is E over and then minus slot. So do you agree with me? So is it okay? Okay. So therefore, if you multiply t here, what you get is that exactly the if you multiply t here and block here, so therefore from here you have the AB log t minus t is equal to ES. Oh, there's some signs wrong. So there must be minus sign here. E somehow sign wrong. As I want. Sorry, this is a minus sign. Sorry, this is minus sign. So therefore this is a plus sign. So therefore this is equal to and this is if you define F, you will get the thermodynamic definition of the free energy. So everything consistent. Everything consistent. Okay. And then last time I made some slight mistake. So CT is equal to del T of D and M. And 1 over infinity MDT squared. Like this way. And plug okay, so then when you solve it so this is MDT, and then this is equal to D over and D over then epsilon mu and epsilon mu squared divided by Z. KDT and mu, and then minus Z squared divided by sum over mu. Okay, like this. So last time I forgot to include this Z, 1 over Z squared here last time in the derivation. But if you compute this honestly, you get the 1 over Z and 1 over Z squared. So you have to, so last time I omitted something. So then this is equal to KBT squared divided by epsilon squared minus epsilon. Okay, so that's what you get. So. Okay. So that's, and this how to say relation allow us to estimate this energy fluctuation. So if you change the heat capacity is that the change of the energy with respect to temperature. So therefore, so the energy fluctuation delta U, in fact, given by this. So energy fluctuation is really given by can be just the relation between energy fluctuation and then heat capacity. That's not true. Any question at this moment? So now I'll move on to ground canonical. Ground canonical. Canonical ensemble. Canonical ensemble. So ground canonical ensemble, and then so it's very similar. To derive a probability of the canonical ensemble, we maximize the F in terms of probability. So in the ground canonical example, you just have the ground potential, which is epsilon, and then this is number. Yes. The procedure is very set. W and 1. Okay. And this one is sum over W, and then epsilon nu minus mu and nu. I mean, it's just a repetition. I'm not gonna spend so much time. And W nu plus lambda s lambda minus lambda. So that's the and we will just try to maximize distance in terms of probability. Okay. And it's 10 exercise. So then W nu is equal to e to the minus nu minus nu n nu divided by kBt minus z, where again z is given by sorry, think it's number. So sorry, this is actually it's 1 over z, so it should be plus and plus. Sorry. So it's a 1 over z, so it should be plus. It's the same. So z is like this. Okay, so like this. Okay, so that's the so the maximum. So maximum is ground potential. Okay. Like this. So then what can you derive that in the same way? We can derive that so I can just reuse the so here we have the so that maybe this is the ground canonical, this is the ground canonical, and then here you have the canonical, and then this becomes omega. Okay, so that's the how you get the sorry, yes. And then similar way, so so this is the ground potential, it's just a kVt. So recall that here so here is the fixed mu, E, and B are fixed. Okay. And the canonical ensemble, do you remember which variable is fixed? Do you remember which thermodynamic quantity is E, B, and B? You don't remember the ensemble. Okay. Ensemble. Okay. So that's the case. And if you do the same computation, you just change this by just adding here. Adding here is minus n minus mu and like this way. And then what you get is that the here yeah, of course, like this way, like this way. And here, what you get is minus mu n. Okay. And then if you use this relation, you will again derive a ground potential is E minus mu n minus ds. That's what you get. Okay. If you use the definition, statistical interpretation of the entropy, you get the thermodynamic relation. Okay. Any question at this moment? Okay, and then the omega cell T. So we derived this one in the last time. So this is a relation. How the ground potential changes with respect to T, V, nu, you get the entropy, pressure, and then number of the particles. So that's how you get. And then if you substitute the previous relation, um, okay, so then the U is equal to 1 over C, G is equal to time mu e to the minus beta is the probability, and it's a nu. Okay? It's a nu. And then you can just add as subtract. And add. Like this way. And then the first of all, this guy is just the derivative of the Johnson potential with respect to beta. And the log plus the first one part, so this part. Okay. And then the second is just the expectation value of number. Okay, so that's the you will get here. And similar to this relation, so the heat capacity, we can just have the variation of the standard difference of the number can be obtained by just acting a mu derivative. So this n square minus n we can have this standard deviation of the number, system number, can be obtained by just applying the derivative with respect to nu twice. I mean, this one, it's the same calculation you can do. I mean, it's very similar calculation as written here. So, but I'm going to skip. It's very, I'm not gonna do all by one. So it's very similar. Okay, so those are the review of the ensemble of statistical mechanics. Any questions at all? Okay. If not, I'm going to talk about a little bit second quantization of the system. If not, I'm going to talk about the second quantization. For this one, maybe I think this one, I don't know. I mean, do you learn this second quantization in statistical mechanics one? Maybe not. Maybe. Okay. Then it's a bit new material. It's very similar to what you learn in quantum field theory, actually. But I'm going to introduce this second quantization from the viewpoint of the statistical mechanics. Okay, so eventually we will learn the superconductivity, and we learn that the superconductivity is to have a fermionic system, like two electrons form a Cooper pair, and then form the Bose-Einstein condensate and so on. So those are like a fermionic, and also so it has a multiple particle, many body particle system. And then so to deal with this many body physics with the like in microscopic world, it's better to introduce so-called second quantization. Um, okay. So in the first context, first, in the mechanics, we just use the Hamiltonian to the operator, which is something like some of this, and the many volume particle. So J. Okay. So these are the so the energy term for a J's particle. J's particle is plus from half sum over D and the interaction. Like this one. Okay. And then so we just solve the equation, something like a del del T psi n like this way, and then I don't remember, is it I or minus I? I don't remember. And H hat acts on psi. So the for Schrödinger equation. And then I put the H bar to be 1, like this. So the first quantization. The second quantization is the case, I mean, so this is called wave function, so psi for wave function. And then this is quantized Hamiltonian, so then this is Schrödinger equation. And the second quantization, we treat this psi as operator. With the operator. With second quantization. Okay. And then second quantization, this is strict, instead of wave functions, we satisfy this equation. We treat this psi as an operator. So and the operator which written in psi at dagger and psi at is also operator. Okay? Also operator we treat psi. Okay. Okay, and then so usually you just write down the Hamiltonian as something like kinetic. So this is the energy for each J's particle and the sum over J. So you have one particle J equal to 1 to n. And this is the interaction term. So usually people just T plus U and so on. So this is the kinetic term, and the U is the potential and so on. And T can be treated as the potential is an operator. EQ X psi. Okay. So those are operators. So we treat this psi dagger of psi as an operator. Now this kinetic term is also operator, which acts on some qubits, right? So operator acts on qubits, right? So that's the idea. And then U is something like and the U hat is something like from top. Then rho hat is this is called density operator. So okay, well, that's the density operator, and then which is written in terms of this wave function. Or I mean, it used to be wave function, but it's a field operator side diagonal. So this is still called Bones. I don't remember Bones approximation. So the Bones expression of this density operator. So these are you learn in quantum mechanics. Roll back. No. No. Okay. Okay. So maybe at this moment you can accept this is the definition of rho. Definition of rho, and then the potential written here is essentially you. So to go from here to here, you sandwich h hat by side side dagger and psi of x. Hat means we treat it as an operator. Okay, so that's the case. And then here I just put some French notation. So double dot right here. This is called normal object. So this is called normal object. So like this. Okay, so here it's normal object means put move annihilation operator. Annihilation operator to the right. And then creation operator. Move creation operator to the left. So that's the move for normal object. Example, if you write down in an example of this oscillator, if you write down a diagram, this means the end diagram. This means that. So you put this is creation operator, annihilation operator, but if you put it inside of this, how to say, double dot semicolon, I don't remember the name of this semicolon. I don't remember. Hey, so put the creation operator to the left and the annihilation to the right. So when you write down learn the quantum mechanics, I'm pretty sure this is still what you learn. That's what happens. People just write down like this. Okay. Some wrongs. People write down like this. Of course, I don't like H bar. So I don't like KB and I don't like H bar. I don't like C. So everything is always, most of the case, I put those constants to be 1. So the reason why people write that like this way is that we want to put the annihilation operator to the right and the creation of the left. If you do that, if you put the atom back here, yeah, if you put the back here, so this term will be gone, and you get the 1/2. E. 1/2. So this time is gone. It's a similar thing. So if you put the normal order, Usually, so the most of the case, in general, so switch operator on in normal order is action vacuum. This is equal to E. Because I put the annihilation of the right and the creation of the left. No, in general, this will happen. But sometimes you have to be careful. So sometimes you encounter some exceptions. Those are you need to pay attention. For most of the cases, this is it. Okay. Fine. Okay. And then you treat a path. So in second quantized form, so you just have operator. H is the operator, which is just a summation distance. Summation distance. H with second quantized. Okay. And then since it's operator, so if you have a psi x and whatever, psi hat x two, somehow you have to be careful about it. The ordering. So as I mentioned, this x2 and psi x1. Okay, so they are not equal as operator. As operator. So you have to determine something for commutation relation. And the philosophy, I'm going to derive in due course. And psi hat, like this way, is given by I times dot of don't have I or something. In dimension d multiplication equals 3, external minus x3. Like this one. So this is called canonical quantization. So that's the canonical quantization. And then you have to be careful about something. So this is only for bottom. And then for permanent, you have to use anti-commutator. So, plus minus means that the A, B plus minus B, A. And then this plus is the bottom. This minus is the permanent. So that's the bottom. Usual case in the half. And then the rest of the other computation relation, like a psi x1, psi x2 is equal to 0, and then the psi dagger that x1 is equal to 0. Okay, that's okay. So those are computation relation. If you treat it as an operator. So, okay, let's look at them very carefully. This is a rough story of what I'm going to explain today. So you start with the classical mechanics and so on. And then when you learn quantum mechanics, you learn the first quantized form of the quantum first quantization, and then learn whatever spectrum, so wave function, so now, so we will use the second quantization to study statistical mechanics. That is you treat everything as an operator. So wave function is the not solution of the Schrödinger equation. We treat it as some operator, and we satisfy this commutation relation. So this is the this. So this is one particle. So here only just consider one particle. System. Okay. So let's try to derive this one heuristically. Okay. Let's try to derive for bosons. So in the and then let's consider the state in particle and state in psi of T, which is something like okay, there's something strange. I think we might actually yeah, Thomas strange. Okay, sorry. Okay, Thomas strange. I think I will change later. The psi, so n is a complete basis. Complete complete basis. So which means that n is the diopter n, and then it's found that this is fun and fun Hilbert plane. Fun Hilbert plane. Okay, then I think identity operator is sum of n. So that's what you learned in quantum mechanics. So therefore, you have a psi, you have n, and n, and I call it this one is the so the point this one is the psi n. And then, so we have a Hamiltonian on psi. Is the Hamiltonian act of psi. And this one can be written as follows: the sum over so this is the case, and if you sandwich by n, like this way. So okay, if you multiply this one, then what you get is that the I delta psi n well t is equal to n h hat psi, and this is equal to sum over m n h. I'm sorry, I cannot write that here. like this one. So this is the matrix element of the matrix element Hamiltonian. Okay? So it's n is usually infinite dimension. N is infinite dimension. So Hamiltonian n and m is a Hamiltonian is a big matrix, infinite dimension matrix, and then you have n and n component is n h hat and whatever. I don't know the convention. Which one is it? Which one is the standard convention? Maybe the other one? I don't know. And anyway, so it depends on convention. So those are Hamiltonian. And then here you have just one by one slash what? Okay. So this is the equation. Okay. Okay, so then Hamiltonian. Okay, so if you write down the ground state energy as a function of the size, so as I mentioned, so the Hamiltonian can be written like this way. Okay, can be written like this way. So if you use this one, so in second quantization, you can write down like this way. So which can be understood as the psi h hat psi. Okay, so this one is the expectation value of h that you understood of this wave function. So then, so here this can be written as psi n star and psi n like this and okay, so that's the case. And then if you plug this one into here, what you get is the following. So I times psi dot n is equal to del h del I times del psi n star. Okay, like this. So if you take the derivative with respect to psi star, you get rid of this one, and you get rid of this one. That is equal to this guy. That is equal to this guy. Okay. I think, yeah, I mean, the form is the opposite. Okay, maybe I should write down like this way and this way. And then, anyway, so I think, anyway, so you should solve m and n. And also, if it's psi star times I is given by minus or psi n. Like this. And I have to put the dot here, so this time derivative. The up dot is the time derivative. And this is very similar to what you have the q dot is equal to the h dot p, and the p dot is equal to minus. Okay. So those are very similar to what you see in the quantum mechanics, or even this last time mechanics. And in quantum mechanics, you put the Q's and P is equal to I times delta and I times delta and delta V. Sorry, I. Okay. I mean, I put the H bar to be 1. So, I mean, if you want to, you can put the H bar, but I don't like it. So I just put like this. So likewise, you impose like this computation ratio as follows. Psi n, psi n squared is equal to delta nm. So that's the, by using analogy of the this is usual computation ratio p, momentum and then position. You can impose like this, and the other is the p. Okay, you understand? Okay. And then if you look at the if you rewrite this equation, in the operator formalism, So here, so in this form, we treat the psi n as a Fourier mode. Okay, we treat this as just Fourier mode. At the level of the Schrödinger equation like this, so this is just Fourier mode. But now, to impose this condition, so it cannot be just number. It cannot be just number. I mean, Fourier model is just a complex number or whatever. Complex number commutes, right? But if you impose this one, it's already treated as an operator. So we treat this Fourier mode to the operator by imposing this computation ratio. Okay. So that's what I did. So this is second quantization. People call this is second quantization. So we treat this Fourier mode as an operator. Now we can just write down the Schrödinger equation as follows. Right? Okay, so we treat like a h hat and then j, and now for this h hat it becomes psi m, m h n psi n, and psi n. Okay. So m and n psi j, like this way. Okay. So this is the I use the here. So now instead of star, so I treat it as operator. So I just change it to dagger because I treat it as operator. That's it. Then so this if you use this configuration, this side dagger. So I should put like this way. Now I should put like this way, maybe as an operator. So this is psi dagger, speed is psi j, and you get the delta mj. Now for what you get is the term of Okay, so that's the operator way of imposing the imposing speed. Okay, so imposing Schrödinger equation. If you want to write down the conjugate, you just have the diagram J. It's the something like this one. Oh, sorry, this is an L. Sorry, maybe I should have an M. Like this. Okay, so that's the conjoint operator. Any question at this moment? So this is the actually implicitly I treat it as a bosonic case. In the case of fermionic case, we just need to use instead of this commutator anti-commutator. So people just write down anti-commutator like this. Like this. Okay. Fine. Um, okay, so that's the proof. So for fermions, you have to use the anti-commutator instead of commutator. Any question at this moment? Okay. So if you want to check this will work, you can do the same exercise what I did here for Fermi. For Fermi. Let's do this. So this is welcome. So after here, so this is the bosonic commutator. Commutation ratio. Bosonic commutation ratio. Boson. Boson is the commutation ratio. And then fermion is the anti-commutation ratio. So let's do one exercise to check this relation. So for fermions, fermion, you have to use the you have to this is computation ratio. That's okay. This is okay. And then here you have to be careful a little bit. So now, so what we need to see is that this one. So to see this one, this part is equal to phi m stagger psi delta L psi j minus phi m stagger psi j psi L. So you can check this is okay. Can you see that? Is it okay? Sorry, not L. N. This is N. Can you see that? Is it okay? So this is the psi dagger, psi n, psi j, plus psi j psi n, and then plus psi n dagger, psi j, and then psi n minus, sorry, this is minus psi m dagger, sorry, psi j, psi m dagger, and then psi n. Is it okay? And then they cancel. And what's left is this content. Is it okay? And can you see that? I just do it step by step. What? I think it should be right. Yeah, I think it's okay. Am I doing correctly? I think. What's the question?
What they are doing is to calculate which one which one.
So this one should be equal to psi n dagger psi n and psi j. I think it's so the two-parametric system will give you one bosonic. Okay? So therefore, it should be commutated. Yeah? It should be commutated. Yeah. But once you see only two, like one, this is like a composite two-parameter is bosonic. So therefore, commutated. But this should be equal to like this. You can write down. And if you use this computation relation, this is gone. This is gone. And this one will give you delta mj psi n minus psi. Is it okay? Is it okay? Okay. So then you get this one, right? You get this one. You get this. If you plug that one to here, you get this one. Okay? So therefore, everything consistent. And that's what I want to show. Is it okay? So what I meant is that this computation relation provides the same the Schrödinger type equation for operand. So that's what I want to see. Any questions at this moment? Okay. So therefore, so this computation relation for boson, this computation anti-computation fermion provides the same Schrödinger type equation for operand. Okay, and then we just want to show the different bases, different computational relation. So let's suppose the something like a psi of x. So this is the wave function is something like that. In quantum mechanics, you learn like this. This one is equal to f(r), those terms. And this one is equal to like this. Okay. And then here, so you can just have the following form. So that and then again you use the x1 is the dx and then x. So this is a complete basis. So you can put this into so then what you get is as follows. A complete basis, and then so here delta nm is the n and m, which is the ddx and x and xm. Okay, so that's the case. So therefore, to get this psi n, so Fourier mode. So now we want to treat instead of Fourier mode, we want to treat it as operator like this one. So to get this operator here, you can use this one to get this one. So this one is equal to ddx and then nx and then psi of x. That's what you get. If you use this one, this relation, and plug this one into here, and you can see that this one is equal to sum over m dx and then nx xm psi m. And since this one is the delta nm, just plug that into here, you get this one. Okay? Is it okay? Do you understand? Is it okay? So this step is very simple. So this one, like delta nm. So therefore you get the side after. The same thing. Side n dagger is the so now I treated this psi of x as operator. EDX. So that's you just have a conflict of this. Okay, now using this one, let's see how this relation looks like. So if we have a psi of x and psi dagger of y, let's see what's going to happen. And so here, let's put the plus minus. So you apply it can be applied both on Fermat. So therefore this one is equal to nm and xm and psi n psi m psi. Okay? So that's what I use from the upstairs. Okay? Sorry, this is y. Sorry, I think I just write down something strange. Yes, something strange. So sorry. So this is xm, this one, and the y m. Is it okay? So this guy provides a psi of x, and this guy who provide a psi dagger of y. Okay. And then, so yeah, I have to put the configuration like this. Is it okay? Okay, now we can use this configuration here. And I've treated as of everything operator. So now And then this one will give you delta Nm. Okay? So which means that this one is given by, in other words, N of y and the x of n and n. And this is equal to, you can just swap this one into here, and this is equal to x and y, which is delta d of x. Is it okay? Is everything clear? I mean, this one is equal to, oh, sorry, what am I doing? Sorry. Okay. Sorry. Okay. Like this. Then since we know that the y is equal to sum of n, it's complete basis. So this is just complete basis. So therefore, you just get inner product x and y. This is just delta function. Okay. So this is both works for both bottom term. Okay. Okay, I think this is another way of looking at the computation ratio or at the freaking operator. Okay, I think a good place to stop. So let's take a break for 10 or 15 minutes and then continue. If you have a question, just tell me.
我试图好好理解这个东西到底是什么。
I don't understand. You mean Chasha Johnson? I just use the. I don't understand the. So I just use this. But I don't. I don't understand the difference between pro function and what's the difference between what's the difference? No, I don't understand the D and then the delta T.就等这个下课再去看到，过一个打一下课就完蛋了，其实你要快说，打错一个，但是我说坐在真正的现场去举起来。
我不知道，感觉都是没讲。真的是非常那个学长，我不知道没有。那是讲那个就是那个多少 ，suppose 那我不知道，我不知道啊，这是别的。全靠原动力和那个这样的力量。
下面相当于是挑一个进去的证据。
Yes,我没有在工作，这个硬核，哎，然后我一开始这个这样的一个。我不会了。哦，这个东西蛮有的，这个我还是太不会讲了，并没有上面太讲什么的。因为我们上个一开始3首歌，对，有一话，我自己的做人，你们可能的翻译啊。可能真的是等在一起，不知道啥意思。你开一个会看，真的很爽。不是，这个中方是真人没有帮真人能搞懂。但是这个中翻翻译完了之后，还有报规范是学习句式调整，他告诉你别来有档还有什么样的会议。这个是在对什么情况？这业务的是对，这个可以放这个是这个。我去看这个图，
对，他们是调的。我刚明白这个题什么意思。这是最一日。这不有发生吗？最一零反对。减号是最一啊，1个对。
对，然后他们，然后真的现在也没有很多，一个这样，对，这个等于这个，对，然后就这个等于这个，哦，然后这个是用这个代，哎，对，跟代码，哦，肯定稍微相反的，啊，是。应该他那个对，刚这个就
就那一堆，我大概看了，但是我没看上。
对 M 的
极限狗。
我操！
我就好像这一会儿过来。
在苹果版下的没有回复这个有点长。可以。
一点的就变成城市。
哎呀，我以为这个做的，这个几国的中间了。
然后单反两边是一个。
那你在苏大的谁在上？
应该是放抖音上有一个。
主要是
这一方面没好。
好吧，对，这
他是好领导。
人物的对吧？这个都告诉大家这个就是然后这个玩法一点，它不是这个圈，但是你死不想玩，它就是没有一个说的起来，一个是往外一个是看我觉得会
是个问题。
我这里啊，对，我这里还没死，然后该一发怎么样？这地方是，然后这边就可以
选吧，不然的上海电视就不看。
不行，
关键没有那么人。然后我讲就做这场的应该是对，咱们实录看是，我觉得是个东西啊。反正他走不走一道，反正后面你们再推，再推，我觉得好像会就是你跟他先 P 到后，再点开一个后，P 到后的分量3，我在一开始这个玩意儿，对，两边一样，我一个一样的，的分量，那我开始能量，那我一样这一点一样，对，这学到，这时间学到，他只能把一样到时都是这接近我一个量的分量的导数和我总数不要是一样。你看这个是，我觉得一个今天像一下子就会了，你跟我有点像，印象会点会觉得是一样，不是在我这边的设计师，我讲的这一点都没得好的这样对吧？这方面还有，你们是不是这个是哪个设计的感觉？就是这个代表，就可以说这里把那个我说那个不好意思。口 bracket 和我，今天你不用我，反正大家都没钱嘛，无所谓。我只是这个男女那两个里面奢华的切换，所以我干脆。院子很多这个东西相关的，你要这个变成会不会传染？然后这个就是点，然后这个其他一样的，然后就是左右两个都是那个一个那个然后就关键就是他们的放在那个我觉得可以，我觉得可以。我可以就是问题，可以就是问题。我是担心的，当然他自己在学，对，这有关系，因为这个有关系，其实因为其实可以有可能比这个要快多，你知道吗？不会啊，这很快的去，技术的时间最早也不一定早，也不一定。你看这样
讲的是那个
这样挺多的啊，其实它会有一些非常严肃。我们电脑这方面小学好像是实验室里的量是这个。不是说还在当这种真没有掉的是吧？那你解的不
安老师大概
不会。你们可以讲，
没错，我们选了一组跟时间无关的。
哦，那你没问题。谢谢。
一点我可以给你。
作业就是。
Where from? Where from? So the English is perfectly okay.我们继续吗？OK。Okay. Yeah. Continue in that case. So some people ask a question: what this means? So this means the NP plus EX. And so this is standard notation. So you should remember. It's really standard notation. So this is equal to A and B and plus. Sorry, maybe if you want the always upper and bottom and the lowest bottom, I should lowest permit, upper and bottom and lowest permit, this should be the correct position. Fine. Okay, so now. Okay, now I just want to write down this way in the operator formula. Operator formula. Supplementarian is like here if you use this one so Hamiltonian can be written like this way. Hamiltonian can be written dx and dx prime. So I just put this one into the x and x prime. So here I just put the phi of x x h hat x prime x prime and like this one. So then this can be written as follows: ddx prime and the psi factor x like this way. Okay, so then this can be written. So this one is something like it's just a denom. So 1 over h squared, or I don't like h squared, so just like done like this way, and then L squared plus u of x and delta x minus x prime. So therefore, if you perform the x prime integral, what you get is that the so now I treated this one as an operator. Now perform the x prime integral, feed this down function, so therefore dx and sine of x and then minus 1 like this. Okay, that's so now we treated the operator, and they are act as a function, like a differential equation on the operator. So those are the fundamental of this system. So this is the fundamental. So now. So we introduced something called the number operator, particle number operators. So in this second quantized form, the particle can particle number is not preserved. So somehow it just like creates an annihilation of a particle up here. So here I use the numbering operator pattern. That's this way. Okay. So then you can just do the computation, use the computation relation. Okay, this is equal to minus L for both on the front both on the front end. So you get this. So I just separate task here already. So when you write down computation relation, this already means that I treated as operator. So then psi is the negative sign, psi dagger is plus sign, which means that psi dagger is the create one particle. Psi L another is one particle. That's why you negative. That's like so therefore this is the this is the more like annihilation operator. This is creation operator. Okay. Yeah, so this means that n of psi L is equal to psi L for the dagger. N minus 1. Like this way. Okay. Okay. So therefore, also, let's look at the previous state of this system. Okay, so the important thing, difference between boson and fermion is this. So the anti-commutator of psi L dagger and psi L dagger is equal to 0. So this is psi L dagger squared. Okay, so therefore, so even though they're creation operator, if you act in the center vacuum of psi L dagger, we just create L fermion. So L fermion, but if you act by outside first, 0, this is equal to 0. So this is exactly the Pauli exclusion principle. If you try to put the two fermions on the L side, and then you get 0. So that is exactly a Pauli exclusion principle. That's why you need an anti-commutator instead of commutator. So if you have a side L dagger, if you have this kind of stuff, this is automatically. Sorry, maybe I should put the clip here. This is automatically because I didn't count for it. But for anti-commutator, this will reach Pauli exclusion. So therefore, the Fock space or Hilbert space or Fock space is that the for boson you can access many times but L. So those are the Hilbert space. For instance, this is N1 and 2 and 3. So this is the number of the particles in first side, number of the particles on second side, number of particles on third side, and so on. Okay. And for instance, you can put that like a psi 1 dagger square, psi 2 dagger cube, psi 3 dagger 0, and so on. Also 0 is something like 2, 3, 0. I just write down, I think. Okay. So those are boson. So this is for boson. For fermion, so this NL has to be 0 or 1. Here NL is a natural number, or you can see. But NL has to be 0 or 1. So therefore, this can be just write down the whatever. And this is equal to 1, 2, 3. Okay. And then, for instance, if you have a psi 1 dagger, psi 3 dagger, psi 7 dagger, and so on. So this is equal to 1, 0, 1, 0, 0, 0, 1, and so on, like this. So the first side, you have a fermion. But second side, there is no operator, so it should be 0. Occupation number 0. Side 3, action here, you create a fermion in third side. And 4, 5, 6, there is no operator here. 7th side, you have a 1 per stop. So these are the fermionic heuristics. It's very easy. Nothing difficult. Is it okay? Any question at this moment? Okay, so then what we have is that the okay, so now here, so let's move back to here. So here this can be written as just a how to say psi and then L and L and psi and sum of L. So instead of doing that, we can insert something like this ddx and then psi of x and x of psi. Yeah. And so you can put like this. And this will give you that the distance is equal to ddx psi over x. Like this. Okay, so that's and this one is the numbering operator. So sorry, this is defining of x. It's called density operator. Operator. So some people ask this is why this is the integral, why this is some discrete term and so on. But I mean, it's totally fine. This L can be written in terms of integral. I mean, sometimes if you treat L as a momentum. So if you have x and L, it's e to the I x L x, maybe minus sign, I don't know. So this is the case. Okay, L is a momentum, and if the space time is the finite volume, finite size, the finite like showing the boxes from integral 0 to L. So the momentum is discrete, whatever. Momentum is the whatever L over integer number, like this integer number. So you can sum over integer. But if you push the space time to infinity, this momentum becomes also the continuous. Okay. So therefore, this dimension, instead of dimension, you have to use the integral. But it's just a notation of the concrete basis. It's totally fine. Okay. So why this is called density operator? Question. Okay. Fine. So therefore, if you use the log of x and pi of x and the minus or plus like this, right? So this is equal to minus plus pi of x delta d x minus 1. Sorry. I think you made a mistake with the y. So that's what can happen. Okay. Suppose we know some region in the, I call it R, some region. There's some physics going on. So there's the energy, non-trivial energy, and there's some wave function, whatever. There may be particle and so on. But outside of R, there's nothing. It's just, suppose there's a vacuum, it's just nothing. So then we can define this number of as of R. It's just the y inside of R, dE y rho y, like this. Then if the operator of psi of x is inside this region, so then we already knew that the distance will give you n hat of R and psi of x is equal to, and if you use the commutation relation, then maybe minus plus, depending on the volume fermion, you get that dy of R psi of x, and this is equal to minus. So this is equal to. So this is equal to minus plus psi of x, where x is inside of R, otherwise 0. Okay. Otherwise 0. Because the integral is only inside the region of R. Okay. So therefore, this will just give you like some flavor of why it's called robo-axis density operator. So inside here, there's something, some whatever. Particle is here, so that if the operator is here, this operator sees the psi of x. But if it is outside, you cannot see because density is 0. Density is 0. Therefore, it becomes 0. Okay, so that's how what happens. Okay, any question at the moment? Okay. Okay, let's write an example of this operator, Hamiltonian operator. In the cubic of length L. suppose you have the system is inside of subatomic. So the bosonic system, which is inside is cubic. Sorry, not cubic, cube. Cube of length L. Length L. Then as I mentioned, momentum is something like a 2 pi over L times IJK, where the this is IJK is inside of D. Inside of D. The momentum is quantized. Okay, and then you can just write down the psi of x. So this is the operator. And now you can just write down the sum over Q. Q and BQ. And this is essentially E to the I E X Q and then BQ. Like this. And then for dagger, you just put the for dagger, I just put the minus sign here, and this is dagger. And then this is Q X like this. Okay. And one can check that the sorry, I have to normalize something. Sorry, I have to normalize. I have to normalize this one is equal to L to D 3 half. 3 half. If you do that, if you consider side x side dagger of y, and this is equal to sum of q and q prime, and then okay, and then is the dq and the dq prime dagger like this. And here you get again delta qq prime. So the momentum has to be set qq prime from this computation relation. Then plug that into here, you will get the you get the 1 over L cube sum over Q and e to the I Q x minus y. And this is what you know about the Fourier now. I mean, if you take this mathematical method of whatever. I don't know the course name, but this is the dot function. Dot function. Oh, that's what you learn. Or did you learn? So this is the Fourier transformation of the delta function. You're okay? Okay. Okay. So then just consider, let's consider free bottom. So then Hamiltonian is the dimension dqx 0 to L, and then what was that? Psi factor of x 1 over L squared to M, like this way. Okay. So that's and this one. you can just plug this expression, that expression into here. And then what you get is a T. Okay, and then sum over Q and Q prime and the H squared, Q squared. I don't like H squared. Okay, so this one is equal to 1 over L3 over 2, sum over Q, and e to the I x Q and dq, right? Is it okay? Is it okay? And then nabla square acts on the here is just you get the q square. Q square. Is it okay? Nabla square just see only this x here. And if you apply twice, you have a q square. And 2s. Okay. And then what you get is the bq prime and the bq. And then e to the I minus iq prime x I x q minus q prime. Is it okay? This is what you get. Sorry, I missed the integral. 0, 1 d qx. Is it okay? Is it okay? Second. So this part will give you this one and this one. Okay. This one give you this part and this one and this part. Okay. And then perform integral dqx dqx. So then it just did this part. The rest is just independent of the x. Okay. And this will give you just the delta q. So this one will give you delta q prime. Okay. Just integral of delta ddx is just give you q has to be equal to q prime. That's the Fourier analysis. And this will give you q for each use is defined. That's it. So this is the Hamiltonian for the free boson in the cube. And so now we treat B as the operator, right? It used to be I call it psi m or something like that, psi m. But now for this particular case, I use B instead of psi. And the B dagger is psi dagger n or something like that. I used to use. Okay, so that's how you get the. So this is a Hamiltonian of this Hamilton operator for free ball. Okay. So far we treated as everything as one particle system. So I'm going to do the many-mode wave function and so on. And then for this one, okay. So that's so when you go to the human face, I use the I already erased the for bottom, so I just put the L and dagger and L and axon vacuum and the product of L and appropriate normalize. So that's what I did. But this is kind of like a momentum basis. I mean, L is more like the same as future, the momentum basis. But now we can just move on to coordinate basis. So the creation of psi act of dagger act on 0 is equal to X. So this is the coordinate basis, one particle state. And for instance, if you just do the following thing, this is just a 0 acts on psi of X acts on here. Okay, maybe I should write down X prime X is equal to 0 acts on psi of X. So here it's just the Hermitian conjugate. So if this one acts on the left, it behave like creation operator. If this acts on the right, it just behave like an annihilation operator. Okay, so then this is the psi factor of X prime and 0. So now, so you can use the computation relations. So this is equal to 0 computation ratio of distance of 0 and then plus I mean here okay minus plus then this is the plus minus and 0 like this. Okay. But this one analyze the vacuum here. This one analyze vacuum here. So second term vanishes. So this second term is gone. And second term is gone. And here you get just delta function. So this is exactly what we want, okay? From this coordinate basis. So this X is the really space-time coordinate, not time, space coordinate. Now, if you have a multiple particle, if you want to consider multiple of any body, so you have x1 equal to xn is equal to psi xn. Maximum back. That's how I define. So here it's like if you have a particle, if you have a space-time, so this is space here, there's the x1, this is x2, this is n, and each position you have some operator. You have operator. So then the auto end of creation operator acts on vacuum will create the end state, end particle state, like this. and you can have an overlap between the wave function and particle state is something like this.
杰克，我那个看我就现在，那看那个
So wave function of any particle state psi. So overlap between this any particle state and wave function. That's how I treat it. So this is wave function. Is it? A wave function of any particle state. Psi. Okay, that's how it works. So this is okay, so that's how it works. One thing I have noticed is that the if it is the identical, so this is psi is identical boson fermion. The fermion. So all those if you consider only identical boson fermion, there's something the symmetry occurs. You can have the sigma 1 if you just swap the operator. Okay. So this is equal to -1 to the so plus minus sigma, where the okay, maybe this is not the right way to, but okay, anyway, so this is the spin static. So which means that if you just swap the position of the position, so if you swap the positional operator, for boson, you always have this sigma is the permutation operator 1 and to the sigma 1 to sigma n. Okay, like this. Sigma n. So that then for boson always that it does matter, even if you just swap the position operator. But for fermion, it really depends on the signature of this permutation. Okay, let's look at the example. Okay, let's look at the example for some simple cases. Okay. Two fermions. Let's see. So now what we are doing is that moving from one particle state to another particle state. Okay, and then just go to the second quantization. That's what we are trying to do. Okay, then so support psi is something like a two-step fermion. A1, A2 would be like this one. So this is the creation operator. Creation operator of the fermion with momentum in okay. And then the wave function, as we know, so it's x1, x2, and psi is equal to 0, so psi x1, psi x2, and then c like here. Okay, that's what you get. Okay. So now to experiment in a cube. Okay, so now we consider the case that the zero psi of x, d dagger of zero is just the integral of dx, okay, dy, zero psi of x, psi dagger of y, and zero, and e to the I cube, sorry, k1. Okay. Not what you get. Okay. Oh, sorry, this should be y. So recall of this case, the psi of dagger of y is sum 1 over L cubed, sum over k, and the e to the minus I k y of b, not b, b k dagger. So therefore, if you do the Fourier transformation for this one, you get the ck dagger. Okay. So there, Fourier transformation with together. Okay. And now we know that this is just to give you delta function of x minus y. Okay. But if you use the computation of sine psi dagger, so this is exactly the same as what we did here. You just get the delta function. So this is equal to L minus 3 over 2, sorry, over 2. Like this. That's what we get. So therefore, we should do the same thing here. We should do the same thing, but you have a two particle. So therefore, this can contract with this guy, or this can contract with this guy. There are two choices. Two choices. So this way of constructing, this is called Wickstrom construction, or this way of constructing. This way of contracting. But the important thing is that if you contract with the bottom one, you don't need to worry about some sign and so on. But if you want to contract with the upper one, so you just need to bring this guy into here, right? Here. But in that case, you have to use the anti-concentration of CK1 dagger, CK dagger 2 is equal to 0. Okay? For example, if you just swap this one here, you get the minus sign. You get the minus sign. So you have to be careful when you treat the fermion. If you swap the operator, you get the minus sign. This is exactly because minus sign here. Okay. then what you get as follows. So this one is that equal to so this guy is essentially equal to x and k. X and k. So therefore you have x1 and then k1, x2, k2. So is it the upper one or bottom one? Upper contraction, bottom contraction. Which one? Bottom contraction. Because x1 is contract with k1, right? Yes. Then the x2 contract with k2. So this. However, if you contract the x1 k2, you get the negative sign because you have to stop the operator. Okay, so that this one is equal to, yeah, so this one is some 2 by 2 matrix, x1, x1, x2, k2, and then. So it's just determinant of this matrix, and this is equal to 1 over L cubed, e minus k1 x1 plus k2 x2 minus e to the minus like this. Okay, so that's the wave function of the two parents inside a cube. Can you imagine how to? Okay, can you imagine how to generate wave function to x1? Can you for n experiment? How do you compute this one? Or what I meant is that just upstairs. So you have okay. So let's write down this one is k1, k2. So k1 also the kn. Can you guess the wave function how to compute? Huh? So you just consider x1, k1, x1, k2, x1, kn. And then here is also xn, k1, and then xn, kn. And what is the metric you consider? And take determinant. Take determinant. That will give you the n per wave function. Okay. Any question at this moment? So far, we consider only the free ones. So we can add that so-called interaction term. Okay, let's go through as much as possible. Okay. Okay. Okay, so the interaction term can be obtained so that in classical interaction potential energy can be obtained by like follows. So this is the density operator. So now we impose the we treat this potential as an operator. So again, rho of x is equal to psi dagger and x psi x. That's density operator. We treat it. So now, so we treat it as an operator. So here it becomes an operator. So these will become operator. This is just function. So b of x prime is just function. But now you have to be careful here. Again, you have it's a creation and annihilation operator. So just simply write down this way is this part is something like a psi dagger x psi x and psi dagger x prime and psi x prime. But now you have to be careful about the ordering, because I mean here it's just it's not just a function, it's just operator. So you have if you write down this one is not equal to psi dagger of x. Like this. Okay. Okay, so then what we need to do is the so-called, again, include normal ordering. So here you just put the normal order. So then normal ordering of this one is indeed equal to like this. So you put the annihilation operator to the right and the creation operator to the left. So you have to, if you put this semicolon inside the semicolon, operator in semicolon, so the always you have to bring this creation operator to the left. So this you have to. Okay, so that's the interaction operator on the in this example. Fine. Okay. Okay. So now, so we just so let's look at some example. Example for how this V hat acts on multiple state. Multiple state. So how it acts on? So this is the operator can act on state. Okay. And then so to compute this one, we just compute the following. So that as you know, this is equal to V hat psi dagger xn dagger x1 acts on bucket. So essentially, what we need to know about how the B hat commute with B dagger of X. And you can compute this one. It's just give you the following thing. So this is 1/2. Is that 1/2? Somehow, what I need to put the 1/2. 1/2 dqy sine dagger like this thing. And then we need to know about how this one commute with the psi dagger of X. So if you look at the only relevant part, psi dagger only C in the computation is C this part. So this part. Okay? Because I mean psi dagger and psi dagger commute. And then so you can just write down y, sorry, y prime and psi dagger of X. So this can be written as the delta y minus X psi y prime plus minus delta y prime of X psi y. Like this. Okay, and then plug that one into here, plug that one into here, what you get, and then perform the delta function integral, what you get is as follows. D Q Y. Sorry. I think I missed the dqy and dqy prime. And then here you get the x minus y and psi dagger of X and rho Y. So that's what you get. So essentially, so if you only look at the here, what's left is psi prime at Y. So therefore, psi dagger of Y prime and psi dagger of Y prime form the rho of Y, and what's left is this guy. On the other hand, for here, if you look at here, the psi Y and the psi dagger Y form rho of Y, and what's left is here. And if you perform delta function, you get this one. Delta function is. So now there is no one half here. The important thing is that these two combine into the one. Okay. So then if you use this one, you can just keep commute using computation relation. Okay. So then, if you consider the following thing, so if you consider psi dagger of xn and psi dagger of x, b hat psi dagger of xj, psi dagger of x1. Okay, and if you swap them, b hat. And what at the cost you get this one. Plus you get the sum of dqy psi dagger of xn. So dot b y minus xj and psi dagger xj and rho of y. And dot x dagger of x1 and e. Okay, so that's what you get. So essentially, so you need to replace this part. So in the middle. Okay. Now, so it's important to notice that so still you will get the psi dagger of xj. Okay. Xj. So now for you perform the cube x integral, what you get is that the here cube integral, what you get is yeah, I have to say one thing. Yeah, so that's the case. And now I want to plot this one. Plot the psi dagger of rho. Psi dagger of xj and rho of y is equal to rho of y with psi dagger of xj plus psi dagger of xi and delta y minus xj. So that's what's going to happen. Okay, and we know I think that I make can take this over. Okay. I think this is not good. It's the opposite. Sorry. Rho of, so this should be minus sign. So this is equal to minus sign. Okay. And if you use this one, so this one is equal to, so here, so we know that if you plug this one into here, okay, yeah. So okay, so I think I should write down here. The plus psi dagger of xj delta y minus xj. So now let's look at this term. So this term, so I just replaced this one by using this rule. Well, it should be okay, right? Yeah, it should be okay. Sorry, I got confused. What am I doing here? So what I want is that this term will give you the it's what desired term, and the rest is the. Sorry, that time is up. Anyway, so okay. I think from here, what I I think I now understand what's going to happen. Sorry. So I just keep commuting lower to the right, and what you get is different. So therefore, what's left? So this part is essentially this part. So this part just give rise to sum of I minus j, b x I minus xj, and x1, and like this. So that's what I wanted to tell you. So essentially, this will create this term. Anyway, okay. So the time is up. I'm sorry. So the last part is the disorder. But next time I will repeat this calculation again at the beginning of lecture. And what you get is the how interaction term acts on this interaction term acts on the n part of this at the beginning of lecture. Let's stop here. So if you have a question, just tell me.
一直在考，这种考试干不了。哎呀，要不是啊。是那不是不认可吗？今天晚上把量的特别小，我说，因为我这在店里我感觉这个也很非这个，我觉得这个最点是我越可以继续这个也不。我觉得我都还有晚了。上面那个太感这样的作业呢，还没复习呢。不行，我没车。我知道，但是我实际上我有点累。这课听着都没太我饿了，被骗进来了。哎，我跟我上学期这样第二的时候，我现在北校看不见。我感觉，那你去北修感觉我不是我不知道，虽然上不了去，我不想去。又不去打理啊！我也想去打理。你们都早上哪儿去了？我早上昨今天凌晨12点没有出现车，下了那个。联想这跟中国比较，主要不想留在非不能也学不起来。我旁边照顾不下去。
And if offer is not
为什么不说开始？为什么？
then you get the offer is not right. Well, so this is not offer. Then when alpha is equal to, then you get alpha of x, and the term and alpha of 1, and alpha of 3. Okay, any other questions? So 开始，你们知道这个规划，为什么规划出来会更好的？更好的原因规划，因为政府方规划，这个是你有，为什么是更好一？为什么一定？不是，我的意思是，因为你有 n 个粒子在重复，你这 n 个粒子的话，你是先产生一个粒子，还是先产生二个粒子？跟你先产生二个先产生，你是一样的。如果你有两个粒子的话，你就是根号二；三个粒子的话，就是三类排列。因为说都 OK 的。下面这一位背离子的话，你有两个。下面这个下面因为你是背离子有两个方面，而你上面是多特异，你相当于你有 n 个根号，就是 n 个根号，相当于如果是不是的话，那就这一项不动，还要再加一项，如果刚好一样，刚好一样的话，这边那个都可以在一起。
which 这边就是一个隐藏的哦，
yeah, or the semi mentioned.
原来是同台北
Officially, I have to come here and down for 1 hour or something like that. Official. Okay. Or every time you can ask before, after the classes. The idea. But of course, we can meet anywhere. Just send me a message if you have questions.
这间教室后面没人。
我也问。
对啊。
都还好奇。
如果是这么混的，这么混的其实
是那个讲一下写哦，对，他从这开始一个列那字儿。哦，我看你的同一个
也
做的在这里是我人家
挨着才
面积非常快。Yeah.我会特别提到费米死的不发生用的现在的那个是
你看之前都没了嘛，
我昨天都晚上左边这个整个
different offering. Different offering. But the form of the competition is the same.
所以那这个方式就有点，刚黑板上讲的，它有2种作用方式。它等于一次量子化等于2种，但是第2种前面有个符号，因为它放的是常识。还有还是这样回事。widely。
What's the multiplication? That's true, but the field operator Hamiltonian, so I mean psi of x is the whatever, the field bottom and so on, but using this one you can create lots more operators. For instance, Hamiltonian, Lagrangian, or this is also operator, and you can just since operator you can integrate all like this way. So they're all operators. We just need to deal with how to all those operators. Yeah.
你的你刚才的 more particle， 就 tree them。
We can, of course, do some calculation. Just use greater in certain cases. That's how we define field operator to grade.
You mean Hamiltonian and so on, right?
Yeah.
Yeah, because the system is described by the Hamiltonian is described by Hamiltonian. So therefore you have to understand how to deal with this operator. That's why it's how this B acts on state. I'm just trying to compute.
So why do we add this token this what is it?
Why?
Why do we have to add all of the possible combinations to?
Why do you need to add?
Why is it that
这个
Why we add these up?
Because there are two ways of doing that, right? I mean, if you multiply, it's just. I mean. 다가 개방. And this creates some tonic fermions with moment on K1, right? That will analyze by the psi of x1, right? And then next is this one expression K2, right? That was analyzed by this one. That's one process.
And there's another.
There's another
So we
process.
add these up because it's. Okay, can we explain this? This? Because whatever these are meaning. So we have two ways. So we add these two ways.
It's similar to like the Nabla like Nabla does a times B, then we run it and
I think we
give it derivative to both A and B and then add them together.
Like two ways to do one thing, but you can't simultaneously.
Yeah, you can go through two process.
Yeah. So we don't multiply this. So we add them up. Yeah. So we add.
It's not simultaneous process.
Yeah. So, it's like this, but not this. So if it's looks like the learning, with the noise. Yep.
还是他也换好了呀？没道理加过去啊，没道理加过去上来啊，没道理，没道理。
No, I mean, it's just the two way of writing. So it's zero. Okay. K1. Side 1. X1. I mean, so this one is equal to essentially x1, x2, k1, k2. It tensor product. So then, so this is x1 plus x2, and then multiply plus k2. The vector space. The vector space.
So we can directly write the
Yeah. So the vector space is the hundred linear. So question?
How can we get this equation? Because this equation, we found that there are four operators, but here we only have two in the also.
Yeah, exactly. And quantization is because sine dagger and star dagger commute, right? We know that we know is sine dagger. Sine dagger. And y.
Yeah.
So therefore, no need to include this.
How can we get this part?
So this is typing. So this computation equal to this one.
Oh, this
So this is type.
If we add the bracket here or we add bracket here, it is the that we all
其实
这个可以唱掉啊，可以啊。
还有都几乎是其实现在心情很不好。
理论是怎么去猜？这大概在纸上，然后上面3
上次我也是这样，这我就为什么发现就是
X，
一定要在我反正
对，这是基础就是到那个做
到时候肯定直接发送 X 主要卖的是被过分。对，一线的时候条件好。
我刚才看了一个3代表3
就比较好。
Then this is equal to 3代表3
提出来的话，也在卖的，双方约定越来越多。
But they commute, right? They commute. Without it,
Yeah.
You know.
这个很多时候都是我遇到的时间丰富的。我还是准备那个。
为什么说这个不可以交换时的这两边问题就
Any other question? Okay. Okay.
哇，这个教室晚上没有课。这个教室我们可以这个一会老师，我们可以一直唱聊到这个晚上10点。
看他在哪号的我建议去一下。其实我觉得第一节会去，第三节会去，看第二节。
因为这个当我
这是我到
这个需要上这个中间理论这个时候，我感觉我两边的话都不会
逻辑上挺怪。
但今天好像没有分，发展。一节课速通2:1，一节课速通20两，接下来他要开始表演。
这是我玩的。
没速通完，基本上快要速。
我的天！但我心想，我小孩有点作业上，这东西不是给算出
对呀。就把他算过的，咱们再自己算一下。他算的时候，咱们就没有完全看，还得自己算，这就是作业。
你有没有做那个讨论？
没什么。
这应该需要注意。
跟我发这场。我说这么一点点。
我
你自己写写。
上课对，上学期我上了一学期的，
你选了一学期的这个。
对，1、2。
这个张老师也给我一个开口，然后啥都会，这个就选对。
自己也写了，但是我感觉别人
简化。
那个录像保存。
讲我的皮质是。
他上会传到 B 站上。哇，对。
不建议说到了地步的话，
为什么其实我刚刚会不会现在它并不是先给我
我来看的话，可能之后处理可能会有这个。
下一个去，下一个去，下一个一定去。
对对，到了，不要说就可以。
这么好。